There are many situations in statistics where we are not interested in the outcome of only a single experiment, but in the combined outcome of a lot of experiments. The most often occurring scenario is where we're interested in the total, so the sum of the dice, or the average, which is just the sum divided by the total amount. Let's start with the simplest example, in which we have two stochastic variables. We call them x and y, and indeed let them represent dice. The dice do not need to be the same. Let x be a six-sided die, a d6 as my dungeon master used to call it, and let y be a d4. If I roll them each on their own, we have separate experiments, and they can be modeled as a space of outcomes 1, 2, 3, 4, 5, 6 for the stochastic variable x, and a space of outcomes 1, 2, 3, 4 for the variable y. And we have a uniform probability mass function as a distribution. If I roll them together, however, then the experiment becomes rolling two dice, and the set of outcomes omega becomes the product space of the two original ones. So omega, the elements in omega form pairs, a pair x, y, containing the outcome for x and for y. And the stochastic variable x now is a function from this tuple to its first element. And the stochastic variable y is a function from this tuple to the second element. But when we write probability of x equals 3, you don't see the difference between rolling a single die x or rolling two dice and just looking at the die x. But what we can do now, that we could not do before, now that we have actually combined the two into a single space omega, is that we can define a third variable s, which is the sum of x and y. So we can also ask the question, how is s distributed if we know the distribution of x and y? Well, let's have a look. The probability that s equals small s is written as the probability of s equals small s. If we look at that set, we see that it's the same set as the one defined by x plus y equals s, which again is the same as the set x equals x and y equals y with small x plus small y equal s. And we can write that as a countable union because there is only a countable number of outcomes s that we need to consider. So it's the union over the variable small x plus small y equals s for the stochastic variable x equals small x and the stochastic variable y equals small y, with every combination of the small x and y that sum up to s. And so the probability of s equal to small s is equal to the sum over all x and y such that x plus y equals s, with the probability of x equal x and the probability of and y equal to y. At this point, our ability to compute further stops because the basic laws for computing with probabilities do not give us anything that we can use to compute the intersection of two sets. We have the intersection of x equals x and y equals y here. We don't know how to continue unless we make use of a property that we actually assume when we are considering the roll of two dice, namely that the two dice rolls have an outcome that is independent of each other. We know that the probability y equals y is the probability that we throw a specific number on our four-sided die. Now, that probability can be split. This measurable set can be split into two measurable sets that are each other's disjoint, that form a disjoint union. Namely, we can look at the probability that x equals x, and that set is disjoint with the set that x does not equal small x. So the probability that y equals y is equal to the probability that x equals x, small x, and y equals small y, plus the probability that x does not equal small x, while y equals small y. Assuming that the probability that y equals small y is bigger than 0, we can divide by it and learn that 1 is equal to the probability of x equals x and y equals y divided by y equals y, plus the probability that x does not equal x and y equals y divided by y equals y. The term on the left of this equation is called the conditional probability that x equals x given that y equals y. If x and y are independent, then this conditional probability should be the same as the probability that x equals x. After all, y doesn't have an influence. So, we can say that the stochastic variables x and y are independent when the probability that x equals x and y equals y is equal to the probability that x equals x times the probability that y equals y. In the more general definition, it is the probability that x is in a set A and y is in a set B is equal to the probability that x is in A times the probability that y is in B. And if you look at cumulative distribution functions, then it of course becomes the probability that x is smaller than x and y is smaller than y is equal to the probability that x is smaller than x times the probability that y is smaller than y. Now this we can use to continue our calculation that we were doing earlier on. We were calculating the probability of this sum s and got to the point where the probability that s was equal to small s is the sum of x plus y equal to small s of the probability of x equals to x and y equals to y. Now this becomes the probability of x equal to x times the probability of y equals to y. And because y is completely determined by x and s, we can also write it as the sum over x of the probability that x is equal to x times the probability of y equal to s minus x. And if you write that at probability mass functions, you get this. And you can do a similar calculation for probability density functions and find this integral, which if you have any formal training in analysis or in electrical engineering, you'll undoubtedly recognize as a convolution, right? So that's nice. If we have independent discrete stochastic variables, we can add them up and then determine the probability mass functions using this convolution. And if we do that for the example of a d6 and a d4, then we get this kind of a distribution probability mass function. If you actually do it for all the dice that I have in my D&D pouch, a d4, a d6, a d10, a d12 and a d20, then you get this combined probability mass function. And you can do the same as well if you have continuous probability density functions. For example, if you combine two uniform distributions, then you get this nice shape. But in the video on stochastic variables, I mentioned that the most generic form in which we can represent the probability of a stochastic variable is using this cumulative distribution function. So what I would really like is if we had a way to not compute this convolution for probability mass functions and probability density functions only, but to actually compute it on cumulative distribution functions. Now, the sad part is that there is no standard algebraic way in which that can be done. But there is a solution. Perhaps if you've had formal training in analysis, you remember that working with convolutions becomes easier if you first make a transition from the time domain to the frequency domain. In other words, if you take a Fourier transform. And that actually helps in our case as well. In probability theory, they don't call it the Fourier transform, they call it the characteristic function of a distribution, but actually it's the same thing. In probability theory, the characteristic function of a stochastic variable is defined as this function phi of t, which is the expected value of a stochastic variable defined as e to the power it of the stochastic variable x, where I is the square root of -1. So it's a complex valued function. An important property of this transformation, of these characteristic functions, is that for any two stochastic variables, the characteristic functions are equal if and only if the cumulative distribution functions are equal. So if we want to find the distribution of the sum of two variables, then we can also look for the distribution with the same characteristic function. We will have to go into some complex analysis for that, but our life is made easier because, well, as you may have guessed from that this is a Fourier transform, when x plus y gives a convolution of the PDFs, it actually also gives rise to a multiplication of the characteristic functions. So the characteristic function of S is the characteristic function of x plus y is going to be equal to the characteristic function of x times the characteristic function of y. As electrical engineers often say, convolution in the time domain gives multiplication in the frequency domain. That wraps up the basics on how to calculate with stochastic variables. Of course, for all these calculations that I've shown, it is important that the variables are independent. And that means that whenever you report on calculations you've made and things you've done with multiple stochastic variables, you need to reflect on whether they are indeed independent. And if they are not independent, you need to reflect on how this may influence your results. If you cannot guarantee independence of two variables, then you may be able to still do some of the calculations, but you have to change them a bit, and that's where covariance comes into play. It's something that will not show up a lot during this module, but it's something that you should be aware about. The covariance is defined as basically the expected deviation of two variables from this idea of being independent. So the expected deviation of x times y from the expected value of x times the expected value of y. If two variables are independent, then their covariance will be 0. But the reverse does not hold. If the covariance is 0, that does not necessarily mean that your variables are independent. See if you can find out an example of two variables that are not independent but have a covariance that is 0. It's a nice exercise.